We shall discuss the variation of pressure with the depth or pressure produced due to fluid depth h and density of fluid is rho. Now see, we consider density of the liquid as rho, okay, and it is in static equilibrium. It is filled in the container which is shown in this figure. We consider a cylindrical element of the fluid. Now this is the fluid as such. This is fluid itself, okay, but the element which we have considered, that is of the cylindrical shape, okay. Now see, we have the pressure at this surface as P1 and pressure on this surface as P2 respectively, okay. Force acting on the liquid column, then force is nothing but pressure into area. So we consider the area of cross section here as A. Then the force acting here on the first surface F1 will be P1 into A, and force acting on the second surface will be P2 into A. Okay. So these are the two forces which are acting. Now the first force which is acting here on the first surface is in downward direction, while this force will be in the upward direction. Why? Because this liquid column, or we can say liquid element which we have considered, is remaining in equilibrium. That is why these two pressure must be in opposite direction. First of all, one is in downward, the other one is in upward direction. Now see, weight of this fluid. Weight of the fluid, as you know, it must be mg, and that must be in downward direction. Okay. Now, as you know that the density is equal to mass upon volume, and volume of this liquid can be area multiplied by length. Now, length of this cylinder is say h, so A into h. So mass will become rho A into h. Therefore, this force mg will be equal to rho A h into g, it becomes. So mg force is equal to rho A h g, okay, and that is written here, okay. Mass is rho A h, okay. Therefore, this force rho A h g, this force is in downward direction. Now see, first force is in downward direction, this force is also in downward direction, and this force is in upward direction. So the resultant force of F1 and W must be balanced by the force F2. So we can write F2 is equal to F1 plus A. F2 is equal to F1 plus A, rather F1 plus W, okay. So F2 minus F1 is equal to W. Now place the values of F2 and F1 and W. So P2A minus P1A is equal to AH rho G. So P2 minus P1, that is pressure difference, will be rho G H, okay, or P2 is equal to P1 plus rho G H, okay. So these are the equations which we have obtained. Now equation 1 shows that pressure difference depends on the vertical distance h between the points 1 and 2, mass density of fluid rho, and acceleration due to gravity g, but it does not depends on the area of cross section, whichever area of cross section it may be, but the pressure difference depends only on the factors, that is rho, that is gravitational acceleration, and this distance between the two surfaces, or we can say the height of the column which we have considered, okay. So it does not depend on the area of cross section. If the effect of gravitation is neglected, say for example there is no gravitational force, then this part becomes 0. So P2 is equal to P1, it becomes, so pressure will be same everywhere. It indicates that if the effect of gravitation is neglected, the pressure at every point in fluid is same. Let there be point 1 on the surface of container. The pressure on the surface is atmospheric pressure, that is PA. Now try to understand this point 1 we are taking here, say for example on the surface of the fluid. So if you take this point 1 here, then the pressure here will be equal to the atmospheric pressure. Okay, so the atmospheric pressure PA is at the top of the surface of the fluid. Okay, so P1 will be equal to PA, and P2 is, say we take as P. So we have P minus PA is equal to rho GH, or P is equal to PA plus rho GH, where P is called the absolute pressure. This equation 3 which we have derived, okay, this is the equation number 3, shows that the pressure P at depth below the surface of the liquid open to the atmosphere is greater than the atmospheric pressure by an amount rho GH. So we can say that the pressure here at any depth, say for example you have the first surface here where the pressure is atmospheric pressure, here this pressure is P. This difference of pressure, that is P minus PA, is rho GH. So the change in the pressure when you go from the surface to a depth of H is rho GH, or rho GH amount of pressure is more here at this depth H. Okay, the excess of pressure, that is P minus PA, how much pressure is more, that is P minus PA, and that is more by rho GH, okay, at depth H. This excess of pressure is called the gauge pressure at the depth. Now explain hydrostatic paradox. Now see, this is the figure which shows different shaped container, but their bottom is connected. Now see, pressure at any point in the liquid does not depend on the shape or area of the vessel. This fact is known as hydrostatic paradox. Okay, so this is the hydrostatic paradox. Consider the vessel of different shape as shown in this figure. They are connected at the bottom, okay, with a horizontal pipe. Now if you fill the liquid here, okay, then what will happen? The height of the liquid is going to remain same irrespective of the shape. This shows that water at the bottom has the same pressure below each section of the vessel. Okay, here the height is same, so at the bottom we have the same pressure on the liquid. Okay, now what is atmospheric pressure? Pressure produced due to atmosphere is the atmospheric pressure. Okay, the pressure of the atmosphere at any point is equal to the weight of the column of air of unit cross sectional area extending from the point to the top of the atmosphere. So the point where you are measuring the pressure is nothing but the pressure which is produced by the air column, which is extended up to the top of the atmosphere. And at the sea level, the value of this atmospheric pressure is 1.013 into 10 raised to 5 Pascal, or 1 atmosphere is nothing but its value, that is 1.013 into 10 raised to 5 Pascal. Now we have a mercury barometer. Okay, this is the mercury barometer which was designed by Torricelli. Okay, this device is shown in this figure. Okay, this is the figure in which the mercury barometer is shown. Okay, this is a glass tube. Okay, and this is the mercury which is filled here. Okay, now the long glass tube of 1 meter closed at one end and filled with the mercury is inverted into a tub of mercury. Okay, thumb is kept on the open part of the tube. So the first we are filling the mercury tube, okay, with the mercury, and one part is kept open. This open part is closed by the thumb. This is completely filled with the mercury, and then it is inverted in this mercury filled container. Okay, then the mercury which is filled inside will slightly come out, okay, in this vessel, and a certain height is adjusted by the mercury in this vertical tube. Okay, if thumb is taken from the tube, level of mercury column slightly decreases. The space above the mercury column in the tube contain only mercury vapor whose pressure is P, and it is very small. Try to understand here. Here, when the mercury is coming out, say for example you have this tube, okay, completely filled with the mercury. Now when you are putting it in a container which is having mercury, then what will happen? This height will be adjusted by itself. Some mercury will come out from this tube, okay, and it will come in this container. So some space will be generated here, some space will be generated, and this space is having no pressure, or we can say some vapor of the mercury may be there, and that is not generating any pressure. So pressure inside this particular space will be equal to 0. Okay, so here the pressure which is generated by this mercury column, try to understand, this mercury column is producing the pressure here at this particular point. Say this pressure is P. Now pressure here, because this surface is open to the atmosphere, and therefore the pressure here at this particular point will be equal to the pressure of atmosphere. And as these 2 points, see these 2 points, this point which is inside, okay, let me show it by a different color, okay, this point which is there inside and this point, they are at the same level, therefore the pressure will be same. So here this mercury column of say height h is generating the pressure that is equal to rho g h, and this pressure which is generated by this mercury column must be equal to the atmospheric pressure, as they are at the same height, the points are at the same height, and that is explained here. Okay, so total pressure at this particular point will be the pressure here at this empty space plus the pressure of this mercury column, that is rho g h. So atmospheric pressure is P plus rho g h, and this pressure here is 0. In this empty space the pressure is 0, so 0 plus rho g h. So total pressure of the atmosphere will be rho g h. Rho is the density of mercury, height is the h is the height of mercury column, and generally we have the adjustment of this mercury is at a height of 76 centimeter, and therefore we can say that at sea level the 76 centimeter height of mercury column, whatever pressure it produces, that is the pressure of the atmosphere, and that will be round about equal to the 1.013 into 10 raised to 5 Pascal. Okay, so you can verify also by taking the value of rho as 13.6 into 10 raised to 3 kilogram per meter cube, and you can calculate rho g h, and that value will be equivalent to 1.013 into 10 raised to 5 Pascal. Okay, so that is done here, okay, which is equivalent to the atmospheric pressure. Okay, there are certain units of pressure. Pressure has different units. Say 1 torr. 1 torr is a unit. Torr is the unit of pressure. 1 torr is 133 Pascal. The millimeter or mm of Hg and torr are used in medicine or the physiology. Okay, these units of mm, or rather mercury height, is producing certain amount of pressure, and that is measured in mm. Okay, mm of Hg, and this unit they are used in the medicine. So mm of Hg is the unit which is generally used in the medicine field, okay, medical field. The bar and millibar are also used in metallurgy. 1 bar is 10 to the 5 Pascal. So bar is another unit, Pascal is a unit, okay. Torr is the unit of the pressure, and SI unit is Newton per meter square. So these are different units of pressure. Now Pascal's law, as you know, that pressure in the fluid at rest is same at all points which are at the same height. Okay, this is Pascal's law, and by using this Pascal's law, how the hydraulic lift works, that is explained here. A change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and the walls of the containing vessel. So Pascal's law is very useful in designing the hydraulic lift, that pressure in the fluid at rest is same at all points which are at the same height, and whatever change in the pressure that is applied to the enclosed fluid is transmitted undiminished to every point of the fluid and the walls of the containing vessel. Now try to understand here. The figure is shown, there are two cylinders having cross sectional area, that is A1 and A2. Here the cross sectional area is A1, and the other one where you want to lift the car, okay, the area of cross section is A2. We can see here A1 is very much smaller than A2, okay. In both the cylinder, airtight pistons are fitted, okay. Now a liquid is filled in the vessel. So this is the liquid which is filled inside the vessel. You can see this is the liquid which is filled in this, okay. Now a piston of small cross section A1 is used to exert the force F1. So here force F1 is applied, and the pressure which is produced here will be P1, and P1 is equal to F1 upon A1 is transmitted throughout the liquid to the large cylinder which is attached with a liner piston of area A2. So the pressure is transmitted here on this second cylinder where the area is A2, okay. So the force F2 is exerted in the upper direction. You can understand that here whenever the force is applied, then pressure is transmitted and force will be acting in the upward direction. Now this, as you know, that F1 and F2 are the two forces, rather force F1 is applied by us externally, and F2 is the force which is transmitted to the second cross section. Now P1 pressure is F1 upon A1. The pressure generated on the second cylinder or second piston will be P2. P2 is equal to F2 upon A2, and according to Pascal's law, this pressure is same at same height. So P1 is equal to P2. So F1 upon A1 is equal to F2 upon A2. So F2 will be A2 upon A1 into F1, and as you know that A2 is very much large than A1, then force is multiplied, or it has become multifold. Okay, you can understand that if 10 Newton force is applied, say for example, okay, here say 10 Newton force is applied as F1 force, and A2 is say 10 times more than A1, then this A2 upon A1 will be say 10. So your force which we have applied, say 10 Newton, will be multiplied by this A2 upon A1, that is 10. So the force acting on the second cylinder, okay, will be 100 Newton. So your force of 10 Newton is multifold. Hence by small force F1, F2 will be obtained, or small force F1 generates large amount of F2. And by this device, car or truck placed on the platform can be lifted easily. Okay, thank you very much. Okay, now watch this video 2-3 times. Okay, and try to understand the topic. Okay, thank you very much.